works, how to control thread lifecycle, how to control execution order, automate tasks around the execution of concurrent tasks, and concurrent management, and ensure memory safety. We will employ different mechanisms to do that: volatile variables, atomic actions, locking. So yes, a variety of different mechanisms that we need to study that help us to properly control concurrency within a Java program. Now, first of all, let's start with some concepts. So what's concurrency, what's multithreading, how it all works, yeah? Thread in a Java program is an execution path. It may involve a series of different method calls, and you carry out whatever business logic you need to carry out within a given thread. Your main method, technically speaking, well, that's just a thread, yeah? But then you can start other threads from within method main, launch other threads if you need to. Each thread can be an object that basically is an implementation of a runnable interface. So imagine you created some class that implements runnable, and runnable interface describes a single method run, and that's where you put your thread actions. However, what you do, you don't call method run directly. Instead, you wrap up runnable object into an object type of thread. So pass runnable into the constructor thread, and then ask thread to start. So what will happen then is a thread scheduler will try to execute the method run, but it will do it in a separate thread from that one of the method main. So method run will be executed at a different thread. What it practically means is that the thread scheduler will try to allocate a portion of CPU time, the time slice, to execute the actions of your method run. And of course, you may have a machine with multiple CPUs, so it's possible that there's some degree of hardware capability of actually executing different things at the same time. But even though you may have like a multi-core CPU and there's some degree of hardware parallelism, you still need to realize that you may launch more threads than your physical hardware parallelism level allows to carry out, in which case what will happen is that threads will start to do kind of time sharing. So there will be a portion of time allocated to execute logic of a run method of one thread on a given CPU core, but then it will have to yield to another thread, so another portion of time will be allocated on a CPU core, and then we'll kind of have to take turns. That's why concurrency is not necessarily means actual physical parallel execution. And so the degree of physical parallelism depends, yeah? And then, of course, you need to remember, your Java program isn't the only piece of software running on that machine. There might be other programs, there might be operating system itself. So certainly the CPU cores could be busy doing other tasks, which have nothing to do with your Java program per se, and you kind of have to time share segments of time on your CPU to carry out your logic. Therefore, how exactly one thread will be allocated time on a given CPU core, and in which order threads will actually perform the actions, is really not predictable. This is a stochastic process. If a particular thread has been launched earlier than another, it doesn't mean it will finish earlier. We can't predict that. We can't guarantee that. It's all the balance of probabilities, because we don't know how physically the time slices will be allocated on CPUs, because we are not in control of this process. And frankly, nobody is, because even a thread scheduler in Java have to yield to other OS tasks that also need to grab the CPU time. Generally speaking, what I'd suggest is a good analogy for what we're trying to do here, how to envisage what that process, feels like. Think about it this way. It's just a comparison, really. Think about what you do in a method run yeah, the logic that you write in a method run, it's like you want to travel from one place to another. This is your algorithm. You carry out a series of actions inside a method run, and you say, and I want to travel from A to B, right? So this is my route. This is my path that I would like to take. So that's the logic of the method run. Now, what a thread is like a car in which you will travel. So you have your route, you know where you want to go, and then you take a thread to actually physically drive, progress down that route. Yeah. And exact same route, exact same logic of a run method can theoretically be passed to multiple different threads. They could be different cars traveling on the same general path from A to B. Yeah. Okay, so you're asking the car to start and you start driving. However, what you need to realize is all of these threads, all of these cars have to share same physical roads, right? So, your CPU cores are like physical roads. You don't build a road per car. That will be rather expensive, right? So each CPU core can accommodate basically that much of traffic, yeah. And then your cars basically have to yield to each other. We say that cars drive on the road simultaneously, don't we? But in reality, do they really? I mean, two different cars can't occupy the same physical spot on the road at the same time. Well, that's known as collision and rather be avoided. So exact same thing happens on a CPU. You can't put two different pieces of logic from different threads to take the same time slice on the same CPU core. That's kind of impossible. They have to yield to each other. Overall, the program has a chance of actually achieving more by loading these CPU cores with different tasks and exploiting the fact that you actually have multiple CPUs or CPU cores. If your program will be single threaded, it will never take the advantage of any CPU core but just one. But of course, if you created multiple threads, now you can exploit the fact that you have these different CPU cores. You can load them with processing, but it still doesn't mean that all of the processing actually physically happens at the same time. So there's some degree of parallelism, but it depends. Okay, so that's just a general concept of how concurrency functions in Java. Now let's take a look closer at how you implement the actual thread. So first, and probably the most common practice here, is to implement a runnable interface, override method run, within which you explore what it is that you want to do, what should be the logic of that thread, and then create a new instance of thread, and pass your class that implements runnable, the object that implements runnable, to a constructor of the thread, and then ask the thread to start. This is kind of the most common, obvious practice. However, thread class itself actually happens to already implement runnable interface. So the alternative is that you can create your class that extends class thread. Because thread implements runnable, that means your class sort of by proxy also implements runnable because it kind of inherits that from a thread, and you can override method run, and you can create an instance of your class. Well, in this case, it extends runnable and thus implements, extends thread and thus implements the runnable interface, and then you can start your thread. But the problem is this is rather inflexible design. If remember what was the comparison I gave you on a previous page, I was talking about the run method being the route and a thread being a car in which you sort of take that route. So you're kind of hard coding the route with the car now. Yeah, you're kind of saying that this car can only drive on that route. Yeah, so that's not particularly flexible. When you have a separate class that implements runnable interface, you may create an instance of that and then decide to pass it on to different threads, start that route multiple times, launch that algorithm multiple times. But here, every time you do that, you actually have to create a new instance of your class, yeah, because each one of these will be a separate physical thread object. Whilst in a common practice scenario where you implement runnable interface, you can theoretically just create one instance of your class and then just pass that one instance to multiple different thread constructors. So you wouldn't have to duplicate that lateral object in memory. Yeah, so there you go. By the way, the name of the class is completely irrelevant. You can call it whatever you like. And finally, runnable interface happens to be a functional interface. It has just one method, run, abstract method that you need to override, run, that's it. So can you implement it as Lambda? Yeah, you can. Right, so you can create a Lambda expression, and well, that's just the same as really implementing runnable interface. Yeah. So for example, if you have a very small amount of actions you want to perform, you don't want to create a full-blown class out of runnable. It's just something that you want to launch as another thread, but that's not a massive amount of code. Then you can, I guess, just embed it into the Lambda expression and pass it to the thread and start the thread. Okay, so these are the ways of actually physically writing the code that will implement the logic of your thread. Now, how to control thread lifecycle, right? So thread could be in these different states: new, runnable, blocked, waiting, timed waiting, terminated, right? These are the possible states in which the thread can be. Transitions between these states are pictured on this page. And what you need to realize is that these transitions, how you can go from one state to another, are essentially limited. You can go from whatever state to runnable state, and from runnable state to whatever other state except new. So new could go to runnable can go to any other state can return back to runnable, well, except terminated, of course, because when you terminate the thread, that's it, you're not running anymore, right? So, for example, what it means, if you want to go from, let's say, blocked to waiting state, just for sake of argument, then you have to transit through the runnable state. So suppose I'm in waiting state, then I want to go blocked, so I need to go waiting, runnable, blocked. Yeah, that's the transition. And when eventually your thread finishes whatever it's doing, I suppose you get to the terminated state. So from there, you cannot really return back to any other state. And before you launched anything, the thread is considered to be a new state, so it's not yet running, and it first needs to transit to the runnable state before you do anything else. So runnable is like a key state of a thread, which basically means it's currently doing stuff. That's runnable state. It's currently executing some logic. Also, you need to realize that all of these actions are not executed with the precision of like nanoseconds. No. When you transit from one state to another, what you need to realize is the thread scheduler has to find a time slot for your thread to do things on a given CPU core. And if your CPU cores are extremely busy, if they're doing stuff, well, there might not be a chance for your thread to do something right now. So there might be a small delay whilst the thread scheduler looks for next available slot of time on a given CPU core. So there's some kind of small delay that may happen. But generally, that's kind of the plot, yeah, of how you can transit from one thread state to another. We'll have to look at the code closer, but so far the example goes like this. You have an implementation of runnable, in this particular case, some Lambda expression, but as I say, it could be a class, right? And then you take this runnable object and you pass it to a couple of different threads. So apparently you can share one runnable object and then physically launch it several times, right? So one algorithm which you want to launch multiple times in parallel. You can do that. You call the start method, and that puts the thread into the runnable state. So from new to runnable, that will happen after you invoke the start. Now, you can check if the thread is still running, is alive, because when it gets to terminated state, well, then it's not alive. But otherwise, it's still alive, right? It might be temporarily blocked, it might be waiting, but it's still alive. So until you get to the terminated state. And then if you want to find out which specific state the thread is in, you can call the method getState and find out what's going on, which current state it's in. Although you need to realize that by the time you get the information about the state, things could have changed and the thread could then go to another state, right? So when you call get state, you would know what the state thread was in at the time when you made that call, but because of the parallelism behind the scenes, the state could have changed since then. So you're kind of getting an information that is not exactly necessarily up to date. Anyway, lastly, what you cannot do, if you started a certain thread, you cannot start it again. So you cannot go from runnable to runnable again. That recursive transition is not possible. Right? So you can go from new to runnable, but not from runnable to runnable. I suppose it's kind of not really a problem because thinking about it, you can just create another thread, right? And use exact same runnable object, pass to the constructor to yet another thread object and just start another one, right? So if you want to start another thread, sure, you can do that. But it has to be another thread. You cannot double start the same one, right? Okay. So next we will take a look at specific transitions. And the first transition I would like you to consider is a transition that takes the thread from runnable state to some other state, like terminated, for example, or I don't know, timed waiting or something like that, yeah? So going from runnable to some other state means that you, well, interrupting a thread, right? And a good example of thread interruption is certainly termination. You know, interrupt and stop doing whatever you're doing. You may think from some perspective that putting thread temporarily to the waiting state is also considered an interruption because, you know, your thread is currently not really doing anything. Yeah, so it pauses for some time, or, you know, pauses indefinitely, whatever, but it's not currently runnable. Now, how do you actually control that? You can tell the thread to interrupt. There is a method you can call upon a thread which says, okay, I'd like you to interrupt. And nothing is going to happen when you call that method. You have to code the reaction to that call within a thread itself. You have to decide what you want to do when you receive an interrupt signal. To write that logic within a runnable object within run method, so remember this lambda expression implements run, yeah? What you do is that you get current thread, thread.current thread. And then with the current thread, you check if you receive an interrupted signal. And you can do it periodically. You can write a while loop and just sort of, you know, check, did anybody ask me to interrupt? Next cycle, did anybody ask me to interrupt, right? So check that interrupted signal. And so you can loop and you can keep checking that. And if you receive that interrupted signal, then you decide what you want to do. And basically, think about it this way. If you reach the end of a run method, you got to the end of the run method, well, that's it. Then your thread is done. It's over. It's terminated. So if you have a while loop and then your thread actions are inside that loop, and then you're checking the interrupted signal, and when you receive it, you decide to exit the loop. Well, if there's nothing else the thread is doing really, then you just got to terminated state. So I guess you can simply return from the while loop, you know, break from the while loop and return from the method when you receive the interrupted signal. And that terminates the thread. But unless you code that logic, nothing's going to happen. You can call the interrupt method, but nothing's going to happen. You actually have to decide what you want to do when you receive the interrupt signal. Now, do you have to terminate the thread at that stage? Do you have to return? Do you have to break out of that loop? No, you don't. Well, you may, but you don't have to do it. So you may decide that you interpret the interrupted signal in a different way. You may interpret that as a temporary pause rather than as actual termination. Talking of temporary pause, there's a method sleep that you can invoke, and you can specify an amount of milliseconds. So 1,000 is a second, basically. So you can put the thread asleep for a period of time. That's timed waiting state. So we're saying to the thread, well, just don't do anything for a while, yeah? However, the sleep method can potentially throw you an interrupted exception. Oh, that's very interesting. Think about it this way. Okay, when you're running state, you keep going through this loop, and when you're actually running, there is a possibility you will check for is interrupted signal, right? Your logic is executed, and sooner or later, that check will be performed. But when you're sleeping, your thread is not running. It's asleep. It's in timed waiting state. So is it currently, when you're sleeping, performing any is interrupted checks? No, it isn't, because it's asleep. You're not progressing through the algorithm. You're not doing anything. So if at the point in time when you are actually asleep, somebody calls an interrupt method upon that thread, what happens then? There is no possibility that your is interrupted code will be invoked because you're not running it. And that's why the sleep method at this stage will be interrupted. So if an interrupt signal arrives at a time when your thread was asleep, the sleep method will interrupt the sleep and will throw interrupted exception. But that's what you do to interrupt a method execution, right? You throw an exception. So you can catch that, and then you decide what you want to do. So essentially inside this catch block, you are reacting to an interrupt signal, pretty much like if you were checking his interrupted condition. It's the same idea. And surely you may take again the decision, what do you want to do? You receive an interrupted signal, but that doesn't mean you have to exit. You may break out of that loop and return from the method, or you may decide not to. That is your choice. How your thread reacts to the interrupt signal is your decision. So hopefully you now understand why there are two types of checks that you perform. You check in whenever you got an interrupted exception. If your thread is not currently running state, that's the only chance for you to know that somebody sent you an interrupt signal. Or you just check is interrupted method. If your thread currently is in the running state, then you know somebody sent you the interrupt signal. If you do neither, then the thread does not react to interrupt signal at all. Okay, now you can block the thread. First, you need to select a monitor object. A monitor object, think about it as kind of a traffic light. So your thread goes to the monitor object and turns it red. Literally, your thread itself turns its own traffic light on. Yeah. So your thread says, I want to be blocked, and turns the traffic light red. What is that monitoring object? What is that traffic light? Well, it could be class. It could be current object instance, or it could be any other object you just select. You can arbitrarily select whatever object you like. So class, current object, or arbitrary object, right? These are your choices. To enter the blocked state, you use the synchronized keyword. Synchronized keyword, if you apply that to an instance method, like this example, public void synchronized A, that will put the A method potentially in a blocked state against the current object, against this. If you're doing it on a static method, that will elect to use a class as a monitor rather than a current object, right? So it'll block your thread against the overall class. And finally, if you just call some method that doesn't have a synchronized keyword, inside that method C, yeah, you may have, or when you call the method C, for example, when you call the method C or inside the method C, you may build a synchronized block, and then you may choose any object you like, which is not necessarily current, just arbitrary object, whatever you want, as the monitor object. So synchronized block of code where an arbitrary object is used as an argument. That basically means you're blocking against that particular object. Now, what would be the runtime reaction to this code? So imagine you run in multiple different threads, right? And they could be different instances of that sum class, for example. Yeah. If these threads are associated with different instances of sum, and you use class, so synchronized against static context, then all these different instances of sum will be blocking each other against the class itself. Because remember, class context is shared between all instances. Okay? If you choose an instance, current instance, to be your monitor, then each instance of sum will have its own monitor, so they will not be blocking each other. However, if you launch more than one thread using the same instance of sum, in between these threads, they will be blocking each other when they are using current object as the monitor. And finally, if you choose to use any other arbitrary object as your monitor, then whichever threads approach that particular object instance will be blocking each other. The reaction to blocking is pretty simple. If two or more threads approach the part of the algorithm that is synchronized against a particular monitor, if these threads are actually sharing that monitor, in other words, if they're on that class or if they're sharing that object, then only one thread will be allowed to enter the synchronized block, whichever one got there first. And then the next thread that got to that synchronized block will have to wait, will be blocked, waiting for the previous thread to complete execution of a synchronized block before it can proceed. Once the thread exits, the first thread exits the synchronized block, completes the synchronized method, that would signal to any other thread that's currently blocked against that same monitor that it can proceed. So if you select, for example, a class as the object monitor, then any thread that uses that particular class entering this static synchronized method will block. Doesn't matter. If you choose the object as a monitor, then only those threads that share a particular object, they will be blocking each other. And threads that are using another instance of that class, they will have their own monitor and they will block each other, but not the first group of threads. Yeah, so you may group them basically. That's as simple as that. Yeah, you may decide which kind of units of synchronization you need. So that allows you to control, to a degree, control the order of execution, because we discussed that already. The order of execution of threads is actually stochastic, right? So you cannot really predict it. But when threads enter synchronized block, well, they have to do it in order. Only one thread can pass through the synchronized block at any given point in time for a given monitor. Now, let's try to make thread wait until notified. That could be an indefinite or timed waiting state. So what is happening here is that we're trying to control, again, the execution order. What if we're trying to do is to put a thread into the state where it just suspends itself. This can be achieved using method wait, which allows you to suspend your thread potentially indefinitely until it is awakened by another thread. Or you may use an overloaded version of the method wait, which allows you to specify timeout, which would allow your thread to resume even if it hasn't received a signal from another thread to wake up. Either way, the important point here is that a thread can use the method wait to suspend itself. In this waiting or time waiting states, thread is just not doing anything. Think about it this way. It's a bit like you get to the crossroads and you turn traffic light red and you're waiting for somebody else to get to the same crossroad and turn it green for you. This is what the waiting state feels like. You stopped and you're waiting for somebody else to turn your light green. So let's take a look at the mechanic of how the actual method wait works. We'll start with electing absolutely any object, could be anything, as your traffic light, as your monitor object. So any object that would be your monitor, could be anything. Then you build synchronized block against this object, against that monitor, and then you invoke method wait upon that object. So your thread now waits against that traffic light. Calling method wait turns the traffic light red. Lovely, then you are now in that waiting state. Now, some other thread somewhere else may take the same monitor object, same instance, and again in a synchronized block, invoke method notify, or you could call notify all, notify or notify all. Methods notify all will cause this thread or multiple threads that are waiting against a given monitor to wake up and transit, from their waiting or time waiting states. So note that it has to be done in a synchronized block against the same monitor in order to be able to wake up that thread. Now, the idea is that if you may have multiple different runnable objects that are waiting against the same monitor, not just this thread, but another thread also waiting against the same monitor. So they're all blocked against the same monitor. And there could be a call to the method notify, which will stochastically notify just one of these threads and tell it, okay, you can now resume. But if you call method notify all, then you will be waking up all of the threads waiting against that monitor, right? So they will all be allowed to resume their execution. Waiting or timed waiting states can also be interrupted by an invocation of an interrupt method, potentially. And this is why when you call a method wait, you have to catch the interrupted exception. Yeah? Because potentially that's another way in which the waiting or timed waiting state can be interrupted. Okay, so that's the idea. The wait notify mechanics allow you to exert some degree of control over the order of execution when you want a thread to pause itself against a given monitor, and then other threads to tell it when to wake up. However, there is a nuanced difference in the way threads transit from waiting and time waiting state back to runnable state. So it depends how did you place the thread into these waiting and time waiting states. That would affect how you transit back to the runnable state. So earlier, we've seen an example using method sleep. Actually, there's an example here as well. Yes, so method sleep that allows you to suspend the thread for a period of time. When timeout of the sleep method is over, all thread is interrupted. It just transits from the timed waiting to a runnable state. This is what we've discussed before. We should know that. But apparently, there is a little bit more to this when you're transiting from waiting or timed waiting states using the wait notify mechanics. So let's take a closer look at these transitions. Let's assume you place your thread into a waiting or time waiting state using methods wait with or without timeout parameters. So next, you want to wake this thread using notify or notify all methods. Apparently, in this scenario, there is a short period where the thread actually goes into the blocked state first, just before it goes into the runnable state. Usually it's a very brief period and may even go completely undetected, even if you constantly poll for the thread state using the get state method. So this is indeed very nuanced behavior, which is often ignored, basically because logically you're invoking notify or notify all methods to put your thread into the runnable state. That's what you want to do. And the brief transition through the block state is just a side effect of await notify method mechanics, the way they're actually implemented in Java. Yeah, so it's just a note that technically there is this extra transition going on under the hood, although logically you're just transiting to the runnable state in your program. Working with common thread properties. A thread could be given a name, if you like. It's just name, call it my thread, whatever, yeah. Okay, what else? Threads do have unique IDs. So you can get the thread ID, which is a number, basically. So you could do custom naming, but it has an ID anyway. Thread could be declared as daemon or user. User thread is default. What's a daemon thread? Well, what's a user thread? Okay, so when you launch a thread, by default, it's considered to be user thread. And the rules go like this. If at least one user thread is still running, then the overall Java virtual machine must not exit. So your method main is a user thread. Whilst the method main is running, your Java virtual machine is still running. But think about it. Now you launched another user thread. You get to the end of the main method. That's it. You got to the end. But your Java virtual machine does not exit. It's still running. It's still running because there's another thread that's still doing stuff, right? And, you know, it's your user tasks that you're doing. However, if you launch a daemon thread, it's as simple as just saying set daemon true, right? You launch a daemon thread, that thread may still be running, but when all user threads finish, even though the daemon thread is still running, Java virtual machine will just exit. So set daemon basically means you're telling Java virtual machine, don't wait for this one. Just don't. Just if you need to exit, exit. Yeah. If all other user threads came to the completion, that's it. You may terminate. So this could be some kind of a background task, like I don't know, background logging or whatever. So something that isn't carrying out the primary business logic of a program, but some kind of utility or service task running in background of your program. And if all other tasks that your program is supposed to complete are over, then you're just happy to terminate and you don't wait for this one to complete. You terminate it and that's that. And you can always check if the thread is daemon or not, yeah. There is also a concept of a thread priority. A priority is a construct which allows you to attempt to control the size of the time slice given to a thread on a CPU. So the thread with a higher priority presumably will get more CPU time than a thread with lower priority. Why did I just use the word presumable? Well, because it depends on your platform. There are platforms where the priority can be controlled with 10 degrees of priorities. One is lowest, 10 is highest. Yeah. But then there are other platforms that don't have that level of control. Not every platform can actually distinguish 10 levels of priorities. So there are cases where you kind of set priority 3 or set priority 4, and there is no difference at all. And anyway, you have to remember that even with priorities, you cannot guarantee the order of executions because you never know. Your CPU could be busy doing something else. And it's just like you drive in a car and you get into traffic. There's little you can do about it. Your CPU is busy doing other tasks. So even if you tell your thread, oh, you're a high priority, well, yeah, but what if some other action in the operation system takes over your CPU? Then it doesn't matter. You still don't get your time slices, right? So it's all probabilistic. You kind of have a chance to get more CPU time, but would you actually get it? Maybe, maybe not. And finally, there is this useful utility method called join. Now, you can do what the join method does without actually calling method join with fairly intricate way of doing that with basically blocking one thread until another one finishes, right? And then you join that same execution path. But obviously, doing all that, wait and notify and synchronize blocks might be handful. So instead, you can simply say, I've got this thread, and I want to wait for another thread to complete whatever it's doing, and then just continue after that. So that's a join method for you. Yeah. Wait for another thread to terminate, and then you proceed, right? That allows you to put threads in certain order to a degree, right? So you can control the order that way by just sort of queuing your thread after another. Okay, now, even though all of these thread maintenance mechanisms are available for you and allow you to control the thread lifecycle, you may quite obviously find them handful to code. So there's a set of classes that help you to automate this process. They're called executors. You'll find them in a Java util concurrent package. And what these executors do, they organize threads for you. So you don't need to write this low-level code that attempts to, start, pause, and control threads and pass execution from one to another. Executors automate that. So what are the executors? Well, you can create various executors using a class called executors and create an executor service objects. So what are they, right? Fixed thread pool. This one allows you to define a pool of threads and reuse them. So you can assign your runnable tasks, for example, to the fixed thread pool, and you say how many concurrent threads you like to have, and then it will just execute your runnable tasks using these threads. It will organize the whole assignment of the thread, a task to a thread, and the whole controlling will be done. Next one, work stealing thread pool. It maintains the pool with a given level of parallelism. The idea is that you were saying, I would like a certain level of parallelism to be achieved. I'll give you some tasks to perform. And if one task finishes earlier, then please take the resources that task was using, like that particular CPU core, and reassign it to be used by another task, right? So by another thread. So the work stealing thread pool will kind of circulate your logic around different CPU cores to achieve a given level of parallelism. Single thread executor, just create one thread. Cache thread pool allows you to create new threads as needed, or reuse existing threads. So you basically pre-create a number of threads and you assign whatever job you want them to do to that pool. Scheduled thread pool allows you to execute your tasks with delay or periodically, or both, actually. And there's a variant of that, which is called single thread, a scheduled executor, and that's doing the same thing, but just for one thread. So you can do it for the pool, you can do it for a single thread. And so, for example, if you need to periodically do something, that's the way to achieve that. Now, what's an unconfigurable one? Unconfigurable executor service allows you to take any other one of the previously defined executors and pools and freeze its configuration. So basically, it allows you to say, oh, I have a fixed thread pool, or I have a work stealing thread pool, whatever it is, set the properties, and then wrap it up into the unconfigurable executor service object, and it will freeze the properties. It would not allow you to change them afterwards. So it's kind of a precaution so you wouldn't accidentally mess around your own configuration. Anyway, so here's an example. We have this runnable task. Again, that's just a lambda here, but obviously it's something that implements runnable interface. You decide what actions you want to perform. This example starts scheduled thread pool. We decided we want the pool of 3 threads. Why not? And then I would like that runnable task here, to be scheduled at fixed rate, right? So there are different ways in which you can do it, and one of them is fixed rate scheduling. And the parameters here define that the task is to be executed every 5 seconds with initial delay of 10 seconds. Okay. You don't need to worry about calling method start, wrapping it up in a thread object, doing all of these, wait and notifies. Yeah, that's just done. Yeah? So that's so much easier. That's an automation. You still need to appreciate what's going on behind the scenes. You still need to understand the stochastic mechanics of thread scheduling, the fact that, well, it has to find a time slot on a CPU, and you have to be respectful of how that is organized. So that means you need to know the mechanics we described in the first part of the chapter to be able to successfully write this logic here inside a run method. But then the controlling part around it, well, that would be done for you by the executor service, which is quite nice. And then finally, what I'm doing here is I'm freezing the configuration. I'm just taking my scheduled executor service and wrapping up in the unconfigurable executor service. Yeah, so from that moment onwards, I wouldn't be able to change its properties. Yeah, so freeze the properties. Let's take a look at further examples. This is kind of a holistic example of showing you the entire life cycle of the executor service. Just because there's no particular reason, instead of the previous example, which was scheduled executor service, I'm using fixed thread pool service on this occasion, just to show you that this is that easy. You can just pick the type, say executors, which type of service you want to create. So this time we're doing a fixed thread pool. Then imagine I've got this runnable component. Again, I'm just doing it as a lambda expression here, and that's a runnable object. Write the logic, whatever you want it to do. And what I want to do is launch it 10 times. Oh, well, that's interesting, because my thread pool is just of 3 threads. And yet I asked 10 runnables to be allocated to that pool, right? So 10 runnable objects, run them within that thread pool, and it's just 3 threads. Well, that's not your problem. It's a problem of the executor service. It will have to time share. It will basically have to do 3 at a time. And it will do 3 at a time. Yeah. So it will grab whatever tasks you gave it and will start executing them. And as the first one finishes, then it will be able to bring in. So it brings in first three, right? Then if one of them finishes, it brings the 4th, and on until it exhausts the 10 instances of the runnable that you asked it to process, basically. So just pass them to the execute method, and that will take care of the rest. To stop accepting new tasks, you can call shutdown method upon the executor. So that basically means that's it, not accepting any further assignments. And then you could define kind of a grace period for the executor to actually finish whatever you've assigned it to do. So that's called await termination, right? Okay. And eventually, when you want to shut down that executor service completely, you use the method shutdown now. So once again, shutdown does not really shut down. Shutdown just stops accepting tasks. It's a very misleading method name, but hey, yeah, such is life. And shutdown now actually terminates the execution. And I guess you want to give your executor service some kind of grace period, just sort of, allowing it to complete the job first. Yeah, eventually, if you got any outstanding threads that are still running, maybe they're stuck or whatever, you can just shut down that entire executor service. Now, on this page, you also have another interesting example right at the end here. So when you're handling call like await termination, you can potentially get an interrupted exception because you're waiting for something to happen. And if your thread that's currently awaiting termination, not these threads that you put in executor service, no, this one that tries to control the executor service, it goes asleep essentially. Await termination means internally there is a code that puts this thread asleep. Well, for 30 seconds in this case. So that means that it can throw you an interrupted exception because somebody else may send you an interrupt signal whilst you've been in that await termination sleeping state, right? So it's essentially timed waiting. Okay, so what happens when you get the interrupt exception? Oh, you decide what you want to do. Maybe you want to shut down that thread pool right now and not wait for completion. I don't know, depends. But there's another interesting piece of code here, which is doing this. Get me the current thread and repropagate the interrupt. Apparently, this is what you can do. When you receive an interrupt signal, you may react to it, and then you may propagate it again. You may say, okay, continue the interrupt signal. Yeah? So because you may have multiple levels of different code blocks, and in some level you receive an interrupted signal, but there might be outer levels where your thread might still be waiting for things. And of course, if you reacted to the interrupt signal on one level, that's not automatically propagated to any other level. So you may explicitly say, just continue repropagating the interrupted signal and signal to anything in that thread, yeah, that the interrupt has been received. But that's up to you. You don't have to do it. It depends on the logic, on the scope of that interrupt signal that you want to achieve. Right, now we've seen so far how we can implement threads using runnable interface. Well, actually, we have an alternative. So runnable gives us the method run, right, which is void method. And you can obviously implement runnable interface, override that method, and tell your thread what you want it to do. Alternatively, you can implement callable interface, which gives you a method call, which returns the value, so it's not void. Apart from returning value, the logic of call is basically the same as logic of run. There's not much difference at all, but as I say, it returns the value. So depending on what you want your thread to do you want it to be like shoot and forget task, then you implement runnable, or do you want it to be a kind of task that actually derives something and returns it to you? Well, then you probably want it to be callable. Okay. However, you obviously need to realize if you're launching a parallel sort of execution path, concurrent thing to happen somewhere, then you can't really tell when it really produced the result, right? The call method, yeah, okay, you can trigger it to run in another thread, but when would that thread finish? When would it return you the value? Well, that's anybody's guess, right? We don't know. It's stochastic by nature. We figured that out already. So there is an interesting trick you can play. The value returned by the call method is wrapped up in the object called future. The way it works is that when you submit the callable object to the executor, so you tell an executor, go and execute that callable, right? Submit it. Submit method returns you the future object immediately. That thread hasn't produced any response yet. It did not return anything from the call method. It probably hasn't even been launched yet. You tell it to submit, and then it has to go and find the time on a CPU to actually execute logic, and then it will start execution. But you get in this future object immediately, before any of the actual execution happens. And there is nothing inside that future object at that stage. It's empty. You're using the generics to describe what sort of return value you expect. So it's basically what your call method is supposed to return, right? You're saying callable of string, yeah? So that's your generic, and the call method then returns string. It doesn't have to be string, it could be any object, it doesn't matter. And then your future object will basically say, okay, I'm expecting a string to be present there, right? So whichever type you expect. And you get the future object immediately, and there is absolutely nothing inside. It's a box that's empty. But the thing is, you're not waiting for submit method to do anything. You continue after that. So when you got this future object, your algorithm just continues. Whatever the submit method is doing goes its merry way, and you go your merry way, and you're doing these things concurrently. Sometime later, you may wonder if the result has been produced. I doubt you want to do it immediately. You don't want to do that result get on the next line of code because, well, it's probably not yet ready. Yeah? So that means before you try to do the result get, think about it, you may do something else. You may do other tasks, you may perform other actions, and eventually when you feel like it, you say, okay, let's check if the result is actually being placed inside a future object. And you call method get. If the result hasn't been produced yet, the method get will block your thread. It will be waiting, basically. So you may describe a time period for how long you would like to wait for the result to be produced. And otherwise, you just call it and you say, okay, well, we're not going to wait. There's probably some kind of problem there. Yeah. But so in this particular case, I'm saying get method wait for 10 seconds. Yeah. And if the result is not available within that period of time, then just forget it. Okay. But otherwise, you just get the value, whatever call method has actually returned. This is a very convenient mechanism. We have discussed that we can try to control the order of thread executions. We know that the general approach to multi-threading, to the concurrency, is that we can't really predict that order. It is stochastic because we don't know which order the CPUs will carry out their tasks. But you may try to control it. However, what you need to realize, trying to control the order of thread executions may lead to locking problems. And these are the typical locking problem scenarios, and they all arise from one premise, from you attempting to control the execution order, right? You're not embracing the stochastic order in which threads are executed. You try to control it. It may be a requirement in your program, I understand, but you have to be aware that every time you try to do it, you're risking running into one of these typical problems. So what are they? The first one is called starvation. You've got a block of code, synchronized block of code. Your thread enters that block and it stays there. What will happen with any other thread that tries to enter the same block against the same monitor object? Well, it will get blocked, right? And if it's getting blocked, then it's not proceeding anywhere. And if your code does not leave that block, then any other thread will just stay blocked. So you literally stop your program dead in its tracks from perspective of any other thread, right? They're not doing anything. They're waiting for you to get out of that block. And if it takes eternity to get out of the block, if you just have a very lengthy algorithm, takes a lot of time to carry it out, well, you'll experience a serious degradation in performance. Yeah, because other threads won't be able to do anything. They'll be just waiting for it. Well, any other thread that uses the same A object, it synchronizes against the same monitor. Yeah. Okay. Next example is live lock. Imagine two threads that are very polite to each other. And each one of these threads is asking the other one, are you finished? Are you finished? And the other one says, oh, no, are you finished? And they kind of form an indefinite loop. It's like, having two people standing in front of the door telling each other, oh, after you. No, after you. And nobody's going anywhere because they just keep yielding to one another. So again, that's a bit of a problem. That's obviously a logical flaw in the algorithm, right? But you may get to this situation if you're trying to be kind of graceful to another thread, and keep checking what it's doing, and that in return is very graceful to you, yeah, and you literally form an indefinite loop here. Okay, well, lastly, the deadlock situation. The deadlock situation occurs when you are using different object monitors for synchronized blocks in reverse order. So, for example, there is one thread that says, I will enter the synchronized block against the object A. Fine, so far so good. And then I'll enter synchronized block against the object B. However, there was another thread that did the exact same thing, but it entered the synchronized block against B first. So that's blocked now. And then it tries to enter the synchronized block against A, but then the first thread already blocked that. So they literally block each other. Oh, and that happens simply because they're just doing it in reverse order. Right? So that's called a deadlock. And again, the program is just stopped and it's not moving anywhere. Yeah, you just stop the program, literally. Okay, well, that's a bit of a problem, isn't it? Here's the real problem. You will have a really difficult time troubleshooting and debugging any of these problems. That's near to impossible. And the reason why it's so difficult to troubleshoot or debug is that none of these problems may happen in a test environment. If your workload is not high enough, if your threads are not competing for CPU time, if there's plenty of CPU time, you may never experience the issue if you don't have high enough degree of concurrency. It's all stochastic. The occurrence of these issues is basically based on probabilities of how many threads you're running, how many concurrent actions you're trying to execute at the same time, how busy is your CPU, how many CPU cores you have, yeah, how busy they are with whatever tasks you gave them. So yeah, you may not experience it in a test, and then it could surface in a production, and again, by looking at any given algorithm in a program on its own, everything may look absolutely fine. You're looking at the algorithm, nothing wrong with that. It's when it interacts with another thread, with another algorithm, that's when you have a problem. So it's very difficult to trace and to find where the issue occurs. And in some of these cases, you may not actually get any exceptions. The program just slows down, or just deadlocks, and you may not actually see any obvious tangible error from it. Or the program goes into indefinite loop. There are no errors. Your CPU is spinning and then nothing is happening, right? So you're kind of wondering what's going on. Well, hey, it could be a live lock, right? So what's the solution to this problem? Well, embrace the stochastic nature of threads. Don't try to control the order of execution. Let them do things in parallel, concurrently, as much as they can, and try to avoid these collisions where you have to ensure that there is a certain order to the execution. That means thinking about the algorithms in a little bit different way, right? So kind of engineering your code in the first place not to have dependencies between threads, to allow them to do things in parallel as much as you can. Throughout the remaining part of this chapter, we'll actually try to address these problems. We'll try to see how we can engineer the program in a way that will allow us not to run into these issues. I'm not saying you will never run into them, that there is still a probability that you write the code in a way that gets you there. But there are certain things you probably want to consider that will allow you to avoid these problems altogether. Anyway, well, let's take a look. So, first issue which we need to consider when thinking about controlling the order of executions is actually memory safety. Okay, so here's the thing. A heap memory, whatever you have in a heap, is potentially shared between all threads. However, each thread has its own stack, so values that are in a stack are not visible to any other threads. Whatever you do in a stack, you can do it in parallel with others, concurrently with other threads, without having to really be concerned about memory safety or data corruption or the order of execution. Whatever you do in your stack, no other thread can possibly see. Yeah, this is your stuff. It's only when you get to the objects in a heap, that's when you have to consider what other threads can see and what other threads can do. Now, the next point is that if your objects in a heap are immutable, if you just read in from them and you don't write to them, then again, there is no issue here. Different threads can read from shared heap as much as they like. They don't really cause any concurrency issues just by getting values. It's only when you try to write into the heap memory, that's when you get a problem. That's when the order of execution becomes important. Yeah. So now we know how to isolate the problem and what we can do to avoid it almost on all occasions. First of all, embrace the immutable design as much as you can, right? Then consider creating copies of objects that will be specific to a given thread that other threads don't look at. So then you save to modify them as much as you like. And then you can synchronize them with main memory. But that means you minimize the impact on other threads. And you allow things to happen concurrently. Yeah, so that's the idea. Otherwise, as I say, you may run into problems because if two different threads try to write to the same memory in a heap at the same time, they might corrupt that memory. And of course, if a particular thread reads from the heap and another thread writes to the heap to the same place, then because these things happen concurrently, what could happen is that they will, you will be reading something that is half written, right? So another thread writes it but hasn't finished writing it, and you're already reading that information, and you got an inconsistent data, basically. Yeah. So these are the typical kind of problems that you have to consider. To ensure consistent access to information, you can use various tricks, and one of these tricks is a use of volatile keyword. There are others, but let's start here. So what a volatile keyword allows you to do. Here's the problem first, yeah? Let's understand what is they're trying to solve, what the issue is trying to solve. Look at this object here, shared object, right? Okay, so if I create a new instance of shared, where is that allocated? New shared is allocated in a heap, and the S is referenced in that heap object. Okay, that much is obvious, right? So we place the shared object in a heap. And then we have here some logic that says while s.y less than 1, blah, 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 do whatever you need. And that's what you're doing inside your run method here, which is what you ask the thread to run. There's another thread that actually changes the values of x and y, yeah, and sets them to a different value. So unless this thread modifies x or y, well, y specifically, and sets y to 2, then this thread, notice it's never incrementing y, right? So this thread will keep on going, keep that loop going, because y is less than 1. Well, it is 0 by default, isn't it? Yeah. So unless another thread sets it to 2, this thread will keep on going. But here's the problem. When you compile this code and when you run it, Java Virtual Machine has a code optimizer built into it. It's called Hotspot VM. But anyway, what it can do is that it can do some optimizations of the bytecode at the execution time. And one of these optimizations, the Java Virtual Machine knows that it's kind of resource-wise not very nice to copy values from heap to stack all the time, right? So what it will decide, and it's probabilistic, it may decide it, maybe not. But anyway, what could happen is that it could take these values, x and y, from the heap and cache them in a stack of an individual thread. So that means that this thread looks at its own copy of y. It's not actually referencing that y variable in a heap, because Java Optimizer just had a thought of, let's cache it locally within that thread that will run quicker. So that means when another thread sets y to 2, actually, it could be that it's just setting its own cached copy. It's not actually modifying the heap memory. So these threads are not looking at the same copy of the variable y. Your code clearly states that it's the same copy of the variable y. That's what you coded. But the reality is that due to the bytecode optimization, the actual virtual machine may decide to have 2 independent copies of variable y here and just ignore the heap altogether, because it's quicker that way. In a single threaded program scenario, that's not a problem. The fact that Java Virtual Machine may decide to grab something from the heap and place it directly in a stack has absolutely no effect on a single threaded program. But it only does on a multi-threaded, because then this memory is not shared any longer. So when you place a volatile keyword on a variable, you force it not to be optimized that way. You force in the Java Virtual Machine to actually keep it in a heap and make sure that any stack representations of that value are actually synchronized with a heap. Obviously, you just turned off the code optimization. So that means your program started running slightly slower because it has to jump from stack to heap every time. But then, when you're changing the variable y to 2, the other while loop will actually see it. Otherwise, it will be none wiser. Yeah, that's the problem. And the stochastic nature of the thread still has to be embraced, because when you say y equals 2, that doesn't mean that the other thread will react to that immediately. No. It's going in a while loop, so it may take some time till the next iteration. That thread may not get the time slot on a CPU immediately. So it will still be some time, few milliseconds or nanoseconds, I don't know, just some kind of not immediate execution. But eventually it will react, because you are now forcing these two representations of variable y to actually point to the same object in a heap, to the same y variable in a heap. Okay, so that's the nature of volatile keyword, basically disabling local caching. What's an atomic action? Well, atomic action is the action that you can perform within a single CPU cycle without being interrupted, right? So something you can do without being interrupted. The problem is that most of the program actions are not actually guaranteed to be atomic, even as something as simple as arithmetic, like plus, plus, minus, minus, or whatever arithmetic operation, right? Even they are not guaranteed to be atomic. A classic example, think about a 64-bit variable on a 32-bit CPU. Well, you may encounter the 32-bit CPU, right? Well, Java is cross-platform, so it can run wherever. And there's no way you can do that in sort of one tick, right? You have to split the number into two, you have to perform the operation in two parts of the number, then you have to combine them. That potentially could take a certain amount of CPU time, right? And you never know, maybe your thread, halfway through this action, ran out of the allocated time slot on a CPU. In which case, well, it will be interrupted. Okay, when it will resume again, it will just continue from the point where it was interrupted. That's fine. So your action will eventually complete correctly. But what's going to happen in between the point in time when your action was interrupted and the point in time when the thread resumed? What if another thread looked at that value? Oh, then you're in trouble, because who knows what that value currently looks like, because it was halfway through the modification, right? Okay, so how to solve it? Theoretically, you can write synchronized blocks around any such code. And then when one thread enters synchronized block, any other thread cannot enter there. Oh, but if you start doing synchronized block around every arithmetic, rest assured, you're kind of almost guaranteeing the deadlock. Yeah, it's a matter of just when you will code to that. Yeah, so that's probably not a very bright idea. And you slow down your program incredibly, because you're causing all the threads to wait for each other. Is there a non-blocking way of achieving the same thing? Well, yes, if you will ask the thread to create a modification, not in a main memory, but in a local cache. It's almost opposite of volatile. Let's take a value from the heap, create the representation of this value, which will be local to a particular thread, so no other thread can look at it. Then you can start modifying it. If you get interrupted, okay. Nobody else can see what you're doing, right? Eventually you resume, you complete your operation, and then the memory can be synchronized with the main memory, right? So from the perspective of any other thread, the action appears as if it's not interrupted, as if it was complete. Although internally, maybe it was interrupted, maybe it wasn't, you don't care. That's the point. And to achieve that, you could use special variable types. Remember wrapper classes like, Boolean, integer, long, blah, 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 yeah? So you've got an equivalent for each one of these, and actually for generic reference as well, for generic object. They're called atomic, yeah? Atomic Boolean, atomic integer, atomic long, atomic reference, yeah? And basically they give you methods that allow you to perform modifications of values. So you call methods such as, for example, increment and get, and that's instead of plus plus basically. So you have methods that are equivalent of relevant operations, relevant operators. And when you call these methods, they are acting as atomic actions. They guarantee that no other thread will see your data halfway through the modification. And you're achieving that without writing synchronized blocks. How cool is that? Yeah? So it's not really difficult to do. It's just that when you have the shared data, you have to consider that anything that you do, apart from probably very basic assignment, which is likely not to be interrupted, but everything else is probably interruptible, in theory. So there you go. Of course, you can use the synchronized blocks to control the order of execution. We talked about it before. Synchronized blocks are known as intrinsic locking. Now, what I would like you to look at in this particular example is a practical aspect of the synchronized block, what it would feel like in real code. So imagine I've got this array list, and I want to be able to add things to that list from different threads concurrently. Okay, well, you can't, with a normal array list, just start adding things from different threads concurrently because that's a shared memory. The add method is definitely not an atomic action. So you will be putting things into that array list, and there will be a high degree of probability that two different threads will attempt to put things at the same slot in that list, because when one thread was putting things, another started putting things as well. The index within the array list hasn't been incremented yet, and then you just corrupt the memory. So you can create a synchronized block and only allow one thread at a time to enter that block. So only one thread at a time will be able to add things to the list. And therefore you guarantee that the list will not be corrupted, right? The only problem is you're kind of slowing down your program at this stage. You're creating a bottleneck. Only one thread can enter that block at a time. But you guarantee the memory safety. So that's the very simple kind of intrinsic lock that you could build. So performance and scalability are not great in this scenario, but memory safety has been ensured. Okay, is there a better way of doing that? Well, apparently you've got automations that allow you to automate this intrinsic locking. Instead of using just array list, which you'd use in normal non-concurrent sort of execution scenarios, you can take that list and you can wrap it up into synchronized list, collections, synchronized list, and pass your normal list as an argument. And then when you add things to that list, you don't need to build synchronized block around the add method, add, remove, whatever, You don't need to build synchronized blocks around these methods. The synchronized list will take care of that. Great. So that's an automation, isn't it? Except when you read from the list. Because when you iterate through that list and you read from it, because the list could be undergoing modification at a time when you are actually reading things, you don't want to read information that is halfway through being added or removed or changed. So that means when you read it from the list, you still have to build a synchronized block around the read operation when you're, when you get in elements and you process in them, right? Okay, even though the list was synchronized, but that only ensures the safety of add, remove, set methods, but consistency of an information you're reading, that is still on you, right? You still have to do it in a synchronized block. Okay, so that was a mechanism that you could use to automate intrinsic locking. So fine. Can you just do it without blocking completely? Well, yeah, you can. Wrap up your list in the copy and write array list. Okay, the examples in this chapter are all in list, but it could be set, it could be any collection, whatever. So anyway, it could be set, for example. Copy and write array set instead. But anyway, you're wrapping up your list in this case to this copy and write wrapper. Notice no synchronized blocks need to be written, because what's going to happen is that every time you try to add to the list or remove or modify the list in any way, a copy will be created which will be specific to your thread. Each thread will get its own copy, and they will perform modifications on their own copies, and then these copies will be merged automatically for you. Wow. And when you read from the list, you just read. Everything is fine. So the only issue here is the size of that collection and the number of concurrent threads. Because if it's really big, then you have to create a copy per thread, and then you risk running out of memory, theoretically. Of course, you're not duplicating the actual objects that are inside the collection. You're just basically duplicating the collection itself, which is only references. But still, sooner or later you run out of RAM, I guess. Yeah. So depending on the size of that collection. But otherwise, it would work rather smoothly without you having to do any kind of bottlenecks in the program multi-threaded execution. You don't have to synchronize anything, right? So that's great. And it embraces the stochastic probabilistic nature of the concurrency, because you don't have to control the order in which they do it. They can do it in whatever order they like. You don't care. Yeah? Okay. Also consider that if you're mostly reading from that collection rather than writing, so the amount of reads is greater than the amount of writes, that's probably the approach that you should select. Because if you write in a lot, having lots of these copies being constantly created and merged, again, will exert certain toll on your CPU. You will be wasting resources on that. Yeah. But if you're mostly reading from the collection, then performance-wise, you should be okay, right? So it's a ratio between the amount of reads and writes that you need to perform. Okay, so now, what if none of these mechanisms satisfies you and you still want to do locking, but you really don't want to do this low-level synchronized blocks, right? Is there an alternative to that? Okay, well, there is, and that's done via a series of different classes available in Java util concurrent locks package. And I'm showing you one example here, which is called reader and read-write lock, but then others. That's definitely not the only type of locking you can achieve. So there's a whole set of classes there that are used to automate the locking. But reader and read-write lock is kind of probably the most obvious one you probably would like to use. So here's how it works. You create this read-write lock object, and from it you obtain a read and a write lock objects. When you're working with this shared resource, let's say this array list is to be shared between multiple concurrent threads, right? Fine. Okay, so when you're doing that, when you're getting values from that collection, when you're retrieving values, you put a read lock around it. You do the lock, and then in the final block, you're doing the unlock, lock, unlock pair, right? And you're doing your reads between the lock and unlock. And if you're reading, just reading, then threads can do it concurrently. They're not stopping to yield to one another. They're just reading. When you're doing operations that mutate the collection, add, set, remove, yeah, so you're modifying content. In these occasions, you could put a write lock. Again, same principle, lock, unlock around whatever action you need to perform. The write locks cause only one thread at a time to be able to actually perform whatever is inside that lock unlock block, right? But they also will, at that stage, stop the readers. The read locks will be paused in whatever read operations. So the idea is that you pause whoever writes, you pause whoever reads whilst you're writing, but otherwise you don't pause whoever reads. And then you only allow one thread at a time to write, okay? So others have to wait for it. And you're achieving that without having to do intricate synchronized blocks or, doing this wait and notifies, yeah? That's much easier, really. So again, it's an automation. Behind the scenes, it's implemented with the techniques we've been discussing throughout this lesson. but you don't need to write kind of low-level code to achieve it. You still need to understand the principles of how the multi-threading generally functions. But when you practically write in this code, you really don't have to get into this really low level of coding. Yeah, you could use these high level APIs that automate the executors, that help you to achieve appropriate locking, or even in some occasions, like this copy and write technique, get away without any locking at all. Yeah. So, okay, there you go. So that's the end of the lesson. However, just very briefly, during this lesson, I kind of interchangeably use the words parallel and concurrent, right? Which terminologically people do, but strictly speaking, parallel means that you really executing something at the same time, whilst concurrent is a more appropriate term most of the time because it implies that you are describing probabilistic nature of something really happening in parallel, or maybe not. So when you code in Java threads, you're kind of thinking, are they really executed in parallel? Maybe if you really have multiple CPU cores and they're free at a time. So yeah, that might actually happen at really same time. But then generally speaking, you probably say, no, well, really, they executed concurrently because it might be at the same time, or they might have to take turns, and it depends on the amount of traffic on your CPUs. Yeah, so there you go. It's just a terminological observation. People use these words interchangeably, but strictly speaking, there's a slight difference in the meaning, right? And you look at the chapter's title, and it's obviously talking about concurrency. So describe how the multi-threading works, look at the thread life cycles and execution orders, automate the management of threads and concurrent tasks, and most importantly, ensure thread safety and memory safety, and try to avoid excessive locking, especially with intrinsic locks. Yeah, embrace the stochastic nature of the concurrency in Java. In terms of what you asked to do during the practice, well, first you asked to write a piece of code that simulates concurrent callers. So, you know, you run in Java SE here, which is just sort of simple command line Java program. But what this practice asks you to do is kind of stretch your imagination a little bit and say, what if I actually have like concurrent invokers simultaneously accessing this product manager object? Well, then I'll have to consider how to properly protect information within it from being corrupted, from being correctly concurrently accessed, right? So that means that we need to consider how do we manage information within that product manager. And the first chunk of this exercise basically performs the analysis of what are the concerns, which objects you need to consider are shared and therefore require extra attention. What are these possible collision points for these concurrent callers within that program of yours? Functionality-wise, what you want to achieve is use the same data in, you know, that map of products here that you have in memory, products and reviews, yeah? But every caller, every concurrent caller should use its own locale. Yeah? So it's like different users, each preferring to use their own language. They jump onto that shared data set in memory and they try to do things with that. Yeah? So we introduce this piece of business logic in the application. What you need to do is protect that shared data cache from being corrupted, make sure you're consistently accessing that, and to achieve that, you need to introduce some kind of lock-in strategy. Yeah? When, for example, you add or remove products or something like that, you don't want that memory to be corrupted by concurrent callers. However, there is one more issue that you will need to solve. Okay, you can create code that protects the shared data cache from being corrupted. But what about your file system? You are reading and writing files, for example, printing product reports. If two different threads will try to print the product report at the same time for the same product, well, they will collide on a file name. So you'll have a situation when they will try to write to the same physical destination, same path on a file system at the same time, and that's going to be a problem. So there are different ways of solving that, but how about just give files different names? You could use a thread identity as part of a name, right? And then you won't collide because you will ensure that every concurrent caller uses its own destination. So this just illustrates the example of thinking not just about what happens in your Java memory per se, but generally what's happening around your program. If you're having an environment where you do things concurrently, then any shared resource is a potential source of contention. And that could be an object in Java memory, or it could be a file in the file system, could be anything really. So you have to consider that when you're writing software that accommodates concurrent callers.